Okay. Should be recording now. Thank you everyone for joining. Today we're going to be continuing this series now in 2023 with a look back at the last year in 2022 with highlights from that year and looking forward into what we can expect in 2023. And I'm going to invite everyone to hold your questions for the end of each talk. And there's a link I'll place for the document here. Put this into the chat. So please feel free to enter questions into this Google Doc. And with that, I guess we'll get started. Our speakers today will be Torre Wenaus from BNL, Graeme Stewart, who comes to us from CERN and the HEP Software Foundation, and Brad Sawatzky, who will be who's from Jefferson Laboratory. And each one will give the perspective from each of their individual labs. So having said that, I will turn it over to Torre to begin with the outlook from BNL. Torre.
Okay. Thank you, Ofer, and thank you also for collecting the SDCC slides that I'll be presenting. And we both have many people to thank who are thanked on a slide at the end of my talk. So yes, I'm going to look at BNL primarily backwards. I was one of the advocates for having more of a forward emphasis this time, but it's hard to go through what's happened in the last year and have much of a slide count left. So what I'm presenting is scoped with the BNL Physics Department Experimental Program in Nuclear and Particle Physics. It's selective, incomplete, a harder cut this year on material in the talk, and the cut being really on emphasis on common software tasks with more information and supplementary slides. So fewer slides than last year, but I still rely on Ofer to give me a warning. So I'll talk about SDCC, the facilities side, then on software, pretty much experiment by experiment, HEP going first this year, and then some cross-cutting topics in data analysis, preservation, AI/ML, complex workflows, DEI, and one summary slide on Outlook. So first, SDCC serves many communities around BNL, but I'm focusing on HEP and nuclear here. And the focus of all of us in the next months and in the next year and beyond is SPhoenix. We actually have a new experiment starting up. It's not every week or every year that we have a new major experiment starting up. SPhoenix is expected to start taking data at end of April. They made really amazing progress, very, very little delay through the whole of COVID, quite remarkably. This will constitute the last RIC running 2023 to 25. STAR will also be running concurrently in that period. And for SDCC, this is a very exciting driver for many developments. SPhoenix will be feeding them data over a 20 to 35 gigabyte data stream from their DAC to SDCC, consumed in a new data center with 3 times more floor space, 5 times more electric power capacity, and tape storage going up by a factor of 3, and ultimately by 2025, a 200K computing core installation for SPhoenix, a substantial enhancement in the high throughput computing facility there. And this will all constitute valuable experience for future support of EIC and HLLHC in particular. So on the online side, with that fire hose data stream coming from DAC to SDCC, there's a collaborative effort to measure and optimize the IO starting at the counting house, support for Luster receiving the data in the center, an offline CVMFS repository, conditions database I'll be talking about from both facility and software angles, the choreography of Penn and Ruzio managing data and workflow for SPhoenix, of course, the hardware, and collaborative tool support, and now federated Indico together with ITD here, and Shift sign up, nice system that originated in STAR. So first, disk storage, distributed and central. Several storage services for a variety of experiments across NP, and Dcache used by several, close to 80 petabytes, over 100 million files. Lustre serving many. It's had stable running with total capacity about 60 petabytes and 500 million files, with an upgrade coming this year that'll bring a new SPhoenix Lustre installation for workgroup users, and will add about 30 petabytes to the existing SPhoenix Lustre, where it's giving excellent streaming performance as needed by that data flow off the detector, and an aggregate throughput of 210 gigabytes a second, with many investigations into various storage technologies informing what goes into production services. On the tape side, we currently 200 petabytes of data in HPSS, with about 70K tapes, new hardware coming in the ramp up for SPhoenix, about 10 gigabyte per second data injection requirement. 2 IBM tape libraries will serve this, and 64 new LTO drives will serve this. And you can see the scary ramp in tape resources, tape capacity that will come over the SPhoenix period. In high throughput computing, almost 2,000 HTC nodes for users, 90,000 logical cores, and HT Condor 9 batch serving them. A purchase of an additional 60K logical cores has delivery expected in February and March, with 20 racks arriving, 10 gigabit NIC, all SSD, lots of memory, 384 gigabytes on these 24 core nodes. All nodes running SL7, with testing and preparations in place for an OS upgrade to Alma Linux 9, and preparing for a Condor upgrade as well. On the high performance computing side, BNL SDCC currently supports 5 HPC clusters, using various hardware configurations for R&D production applications. The largest of those is the institutional cluster, with several hundred nodes with various GPU configurations, much NVIDIA. Then 4 others. The news right now is that we have spent the last year settling what's going to be the makeup of the second generation institutional cluster. And an order has now been placed, and it will have 4 NVIDIA A100s with lots of memory per node. And overall, it's going to bring a performance boost of 3 times relative to a current institutional cluster node, about 25 teraflops as opposed to 8 teraflops in the first generation. OKD, which is an open source variant on Kubernetes. I think it comes from Red Hat, but it's used here for Kubernetes purposes on Atlas. It's used for the analysis facility that I'll talk about in a moment, where it supports Rihanna, that I'll mention a few times, that is a service for reusable and reproducible data analysis platform, important to data analysis preservation and used in active analyses as well. ServiceX, an analysis data transformation system, and Jupyter Hub I'll mention in connection with the analysis facility. Doesn't require Kubernetes, it can use Kubernetes. It uses batch, same for Rihanna. On SPhoenix, we have now, for the first time for Panda and the conditions database, we have OKD Kubernetes-based service support for them. So both Panda and the conditions database supported by OKD services, and the Panda developers have adapted Panda services to do this with use of Helm charts for automated, reproducible, low maintenance installation of services on OKD. It's a nice example of a collaborative effort in deployment and support between developers and users, the collaboration between SDCC and NPPS, the software group, with SDCC managing the OKD software and hardware, and the conditions database and PANA deployments maintained and managed by the NPPS group. So to the analysis facility, this is a shared pool used by Atlas users for batch analysis, with over 10K cores available and occasionally utilized in full opportunistically. Kerberos authentication to CERN EOS now very nice, so can gain local access here to CERN EOS on interactive nodes. Jupyter Hub, a very important service in the analysis facility makeup, with now federated login capability, accepting credentials from CERN, Fermi, Slack, and providing lightweight SDCC accounts for a low bar of entry to people to get in and use it, with a Lustre deployment that's new this year, serving storage needs for analysis files. So in 2023, expanded performance capability will come. Dask is something we've been investigating in a number of contexts for distributed processing, parallel processing. Iris HEP has an ever-growing tool set, ServiceX being one of those that are being exercised in successive grand challenges that we are involved in. And an automated build service for custom user containers will come as well. So that was a very fast survey of the facilities side. I'm turning to the software side. Most, certainly not all, of the software activity is consolidated in the NPPS group, Nuclear and Particle Physics Software Group, which now has 23 nuclear and HEP members working on 10 experiments overall across NP and HEP, where the emphasis is in cross-experiment common software efforts across HEP and NP, sharing personnel expertise and software. You can see that in the fact that 19 members of the group are working on more than one experiment. A strong CERN-based team we gain a lot of benefit from. This is Atlas folks and also Intensity Frontier, mostly Dune folks, and many collaborations wider in the community. So turning to what we've done in the last year and are planning over the next year, Atlas Distributed Computing, and the focus there being moving towards HLLHC is our largest activity, centered around our largest product development activity, which is Panda, and not going through the details, which I've done in the past, emphasizing what the emphasis has been on Panda development in the last year and ongoing into 2023 is on analysis functionality. So improving ease of use for analysis that extends to interactive and pseudo-interactive analysis, and not only batch-like analysis. Jupyter has been integrated as an environment in order in which to do Panda work when, of course, you want a more interactive experience. The Panda monitor also extended to provide more interactive functionality. This demands a faster system top to bottom, so latency reduction has been a focus throughout the system, such as using more message-driven internal communication. You need to be using the right resources, fast turnaround, fast ramp resources if you're going to do real-time or near real-time processing. So PandaQ and site ranking for utility for analysis, fast turnaround workflows, and really most importantly, leveraging platforms that aren't grid platforms like Kubernetes and clouds, and then can give you the fast spiking into large resources to be able to turn around workflows, analysis workflows quickly. Complex workflows has been AI/ML and other related complex workflows that, time permitting, close to the end, I'll say a bit more about. And these complex workflows in particular depend upon Panda's companion in recent years, the Intelligent Data Delivery Service, IDDS, which is relegated to a supplementary slide. So looking at Panda, at Atlas distributed computing highlights and plans, containerization has been a big focus, in particular to serve these Kubernetes OKD-based installations of the Panda service. I mentioned already the BNL one for SPhoenix. Another one I'll be mentioning happening concurrently, which is extremely helpful for doing things once and not twice, is the same sort of setup as being used at Rubin and Slack. But this has been a big effort and part of the Panda team to move to full containerization of the components. And Postgres in the back end has also been a big change. Panda has run for many years on Oracle, but nobody wants to use Oracle outside of CERN, so both at Slack and at BNL. Postgres is in the back end, and moving towards production, this will be a new experience and comes along with, for example, new database scheming versioning to keep it all consistent across instances and technologies. With the new people we brought in that I'll mention in the context of the Rubin work, we, for the first time in a long time, have a core Panda team that spans the Atlantic. So making sure everybody is properly plugged into a now very distributed core team has been an important activity that we did last year. Data carousel, I talked about last year, using a sliding window of disk resident data to process with a very small disk footprint, a data sample that resides on tape, has been in production for a few years now, but we're entering a new R&D phase on this. Data carousel will work better if we're intelligently grouping associated data. So smart writing is a big challenge because every tape facility has their own ideas on how to do that. And then deleting less popular data and recreating data on demand is actually something that we'll be trying out very likely in the next year. I mentioned complex workflows. One specifically is using FuncX, which is a new component of Parcel to leverage DOE's big GPU-rich LFCs. We've added support for a number of workflow definition languages, and we're working on adding another one from SnakeMake, Python-based workflow description. These are very popular and useful for integrating different workflow components with Panda. Sustainable computing is a very interesting new thread. We're working to set things up to be able to show CO2 emissions for Panda workloads, exploring elastic resource usage based on electricity price and integrating green resource providers. And you can click on Lancium to learn about one of them. Then we've been asked for and have wanted ourselves for a long time the definitive Panda paper, and it's actually now in advanced preparation. And an IDDS paper will follow. Google R&D project. This is the second phase of what was a successful first couple of years working with Google. Second phase that's about to launch, continuing some of the themes of the first one with expanded goals in exercising, in particular for analysis, the tools and capabilities of the Google Cloud platform, like various architectures, ARM, GPUs, FPGAs, high memory or high CPU capacity, large databases like BigQuery, the ability to spike into Kubernetes cluster with on-demand scaling, Jupyter at the front end, Dask at the back end, storage with S3. All of these things fit well the analysis model in the first round, so we're doing a more extensive round, and in which another goal is to make a fair comparison to traditional resources of Google as a conventional Atlas site. Can we really use it as such, and what's the relative cost of ownership? The scale of this, about 10K virtual CPUs over 18 months. Turning to offline software, we have a small but very impactful team working in this area. They've been instrumental in the major objectives for the offline software for Run 3, which is getting the multi-threaded framework into production, and a new Python-based configuration system that leverages what's now 20 years of experience with Python-based C++ config to have a next generation system. The full Atlas software stack is ported now to ARM. And that was a very good investment of time of folks on our team. We have our HPCs based on ARM coming, and now we know we can do the full software stack on them. It even works on your Apple laptop, M1, M2 laptop. Compact formats are a major element of the HLLHC storage challenge. We've been central in planning the analysis model that uses them and in implementing them. A very interesting, promising next step is the RN tuple format being developed by the root team for analysis formats. After a prototype round last year that was promising, this has now been expanded to a full-scale persistent storage technology backend for the Atlas analysis formats, handling all Athena Atlas framework data types, with further collaboration with the root team ongoing on improvements and extensions. Also working on adding AI ML capability in the framework to support ML-based algorithms. You can see the plot there of factor 3 reduction in the memory, which is the real win, material win from a multi-threaded framework in the Atlas experience. Software infrastructure, I'm sure I'm needing to go quicker than I am, so I'm going to be very light on this, but summarize here is the very busy year in this area with 30 nightly branches testing the many new platforms and compilers that we deal with, both in local and larger scale grid testing. There have been important improvements in this in the last year, like using the very large array. You can see the build farm of remarkably 1,300 cores, using them efficiently, both for continuous integration and nightlies.
And just a heads up, Torre, we got about 5 minutes to go here.
Yeah. So in Rubin, it's been a busy year of improvements. Did I skip? Yes, I skipped. So in Rubin, after Panda was adopted in 2021, we filled out the team with 3 new hires in 2022, and they've been working hard on production, integration, and looking at new potential work cases, use cases, of which a really interesting one is prompt processing, analyzing the of order million objects per night that show a change, so you have to notify the astronomy community. We got through a production campaign using Panda successfully. The extensions we're putting in benefit both Atlas and Rubin. For example, real-time logging or near real-time logging. I think because I'm late, I'm going to skip over Rubin's slide 2 and mention that we have 2 more astrophysics experiments now. Dark energy science collaboration, which will use Rubin LSST data. We're working in computing operations on production, improving performance of the production system, analyzing its weak points, and out of that study coming the initiation of developing a new desk prod higher level service to manage the parcel instances that are the base of the production system. In Lucy, this is a radio telescope to be landed on the dark side of the moon, so a very quiet environment electromagnetically, looking at very low frequency galactic and extragalactic radio astronomy. And we're working in many aspects here, but I want to mention how here we also have a case of experience benefiting in both directions, that the work we've been doing for them on Python bindings for their C++ software, we're also now deriving benefit from in looking at Python bindings for EPIC and EAST in the EIC realm. So Dune, the data prep framework, we've been working on a mini framework for initial processing and data. This and our conditions database work will be important for proto-Dune, no payload DB. I will mention in a moment in the context of Bell 2 that it's originated in. This no payload DB we developed is now represented in the database design in the conceptual design report document. In Bell 2, distributed data management, Ruzio is a major player in Bell 2. Bell 2, a major stakeholder in Ruzio, actually even bigger than CMS with an order terabyte database, making lots of strong contributions to the Ruzio community. Ruzio in recent years has had extended functionality as a user-defined metadata store. So Bell 2 is looking at taking advantage of that. And a new project this year has been on the software infrastructure side to help Bell 2 move from the Atlassian stack, in particular Jira, Gitstash, to GitLab. This has been a tricky piece of work, a very nice piece of work using the APIs on both sides to their fullest to do a full automatic migration. And this developed and was executed over the last 3 months. Finally, with no time left, moving to nuclear, and the conditions database that I mentioned was developed in the Bell 2 context was first generalized to experiment agnostic as the no payload DB, and then we're applying no payload DB to SPhoenix. As I mentioned, Dune looking at it too. We expect to migrate Bell 2 to it, and P4HEP, the CERN-based software stack, has also expressed interest. And this has been discussed in the context of the HSF, where the condition database discussion goes back years, and there's discussion now of using this as an HSF reference implementation. I won't go through the technology stack used there. SPhoenix tracking based on ACTS has come from our group. And this has been a key effort, of course, in the software preparations for SPhoenix. That has gone well. It's had a challenging job to meet the memory and timing constraints, as well as the tracking performance constraints. These are under control with ongoing efforts to improve the performance, and continuing to work with the ACTS team on new tools and features. And of course, the work shifting to a focus on commissioning now. In SPhoenix processing, we're leveraging Panda and IDDS here with a tool layered on top called Shrek that works with both Panda and Ruzio. Ruzio to as the data catalog and discovering new data and dispatching reconstruction through data appearance in Ruzio, and then the full simulation chain from event generation through RICO has been demonstrated with the Shrek layer thus far. The ultimate objective is to use a BNL, this new BNL-based Panda instance. It's up under test. We still need a production level Postgres. In the meantime, we're using the CERN R&D instance of Panda. In EIC software, I'm largely going to leave this to the JLab folks who have been extremely active in this area. We've had our activities in the EIC software, the busy year that went on in 2022. But you'll be hearing more about it from JLab, so I'm just going to zip right past that. Into some of the cross-cutting ones, data analysis preservation has always been a focus of ours, drawing on the very rich CERN and community software services stack. Phoenix, a long-term activity in data analysis preservation, with an ongoing analysis now successfully ported to Rihanna, and ever increasingly populated HEP data, and in ever increasing population of documentation in Zenodo, including now all PhD theses. FAIR OS HEP. This is a new research coordination network being established with the NSF, and I'll just leave it that this is a new initiative that we look forward to participating in the coming year, with a formative workshop coming at CERN next month. SPhoenix is mandated to give early attention to DAP, but of course their attention is pretty occupied right now. And EIC, to their credit, has really started looking at DAP from the beginning, with it being one of the areas looked at in the software planning process that you'll hear about. Large-scale complex workflows. So suffice to say that a theme over the last year and definitely into the next year has been how can we leverage our capability in PEN and IDDS in complex workflows to support analysis, to support machine learning, and combining those two together has led to a new related type of workflow, active learning, out of work from our NYU and other colleagues. And we've been exploring this on the high energy side over the last year. An interesting possibility has come up in the recent months to possibly explore it on the nuclear side. Also, in particular in AI-assisted detector design, where the EIC has really been in the lead in AI-assisted detector design. And our complex workflows could fit right in. So we'll see how that goes in the next year. We're all related to that. We're planning collaboration with CSI on using FunkX to send workloads to the DOE large supercomputers, which are nicely tuned to accept machine learning workflows, unlike Atlas production workflows, for example. So DEI, this has been, of course, is a focus at BNL and everywhere, increasingly. Our increased attention to DI really paid off in the last year when we, with the support of HR, resolved to be more accommodating of working history gaps. In other words, time away from the workforce. This has already paid off very nicely. COVID brought the possibility for fully remote work, which opens our pool of candidates for jobs. So does our strong presence at CERN, and in increasing the pool is a very important part of increasing diversity. Mentoring and training, we're involved in BNL programs like software computing speaker contributions to the summer lecture series we have here, and an interesting new round of DOE funding for computational HEP training will be involved in. At the community level, I don't have to describe to this audience HSF and Chapman related. So finally to 2023. SPhoenix data taking, I mentioned HLLHC readiness is ramping up, even as the HLLHC start date recedes, unfortunately, but the computing TDR is out there and we're working on R&D demonstrators towards technology decisions on that. The exciting new phase of EIC that it's entered with detector collaboration established. Our software effort is small. Our bosses tell us we can't afford it right now, but we have activities expertise to draw on, and we'll have the SPhoenix experience to draw on as we go forward. We'll see what new opportunities pop up. We weren't expecting Desk and Lucy in the last year. And the analysis tools focus I've mentioned, and AI/ML and data analysis preservation. So that brings me to the end with many people to thank. Thank you for your attention.
Thank you, Torre. It's always breathtaking to see both the breadth and depth of the work going on in these groups. I mean, it touches on so many topics. So thanks for trying to get that through that as quickly as possible. We've got a couple of questions in the Google Doc. The first one I see is asking about how the selection of Linux distribution for these clusters is going. I don't know if you want to address that.
Oh no, you can take that.
Okay.
Pass it.
Yeah. So in a nutshell, for those of you who have not followed, a year and a half, about a year and a half ago, Red Hat kind of changed their support and release model abruptly. And this sort of sent the WLCG world into a little bit of a turmoil. And so there's been discussion going on under many different umbrellas for how to proceed with Linux distributions at the facilities. At some point, we were looking at CentOS Stream for this. But experience at CERN on that was not so great in terms of the handling of updates and things like that. So The latest news on that with discussions under the WLCG, and most recently, there were recommendations that there was a joint recommendation that was put out by CERN and Fermilab that basically recommended two options. One is the Red Hat Enterprise Linux, and the other is a RHEL clone. And all the RHEL clones like Rocky Linux and Alma Linux in particular are kind of bit for bit compatible with RHEL. So that's considered acceptable for any of these sites. At BNL, we had been looking at Rocky and planning to go that way, but it seems that most of the community is moving towards Alma based on, more their organizational structure and support structure, I think. So that's starting to look like how we're going to be going at BNL. Now, there's a question about going to version 8 or version 9. The current plan, I think, for a lot of sites is to skip 8 and move towards 9, and we're just waiting for some of the middleware to be ready for that. So I know, Jan, if that answers your question sufficiently or not.
Yes, I think it did. Thank you.
All right, great. Thank you. And Torre, we had a question from Graeme Stewart about the IC clusters and their use. I think this might be good. I see Tony Wong is connected. Tony, maybe you can try to field this. There's a question about how much of the GPU power on the IC cluster currently gets used and by which users are primarily using it. I know you work with that.
The current IC system, the GPUs are primarily used by the LQCD community. So the main users are, you could argue, were here at Brookhaven are the LQCD community, the CFN, the Center for Functional Nanomaterials at Brookhaven, and then finally the Condensed Matter Physics and Materials Sciences Department in Brookhaven. So there are smaller components being used by the Phoenix experiment from legacy work, as well as Atlas. But over 80% of the GPU usage on the existing cluster is done by the LQCD community.
All right, thanks, Tony. Graeme, does that answer your question?
Yeah, very much. Thanks a lot, Tony. I was just intrigued. I was wondering if we had some secret HEP use that we weren't aware of, but evidently it's from other communities where GPU workloads are a bit easier.
Yeah, we're hoping and expecting to see a ramp up in HEP, in particular from Atlas at some point. But yeah, we'll keep you posted. I see that Attila, you have your hand raised. You'd like to ask a question?
Yeah, I wanted to follow up on this. I was curious if these GPU users were mainly doing it through a batch system or more interactively, or what was the pattern mainly?
It is batch system. They are using Slurm, and they're not using HT Condor. So it's a specialized Slurm batch system that's primarily tuned for these kind of systems with a high, low latency interconnector. So all these systems are connected with InfiniBand.
Oh, I see. Okay, because as was said, we hope that Atlas at one point will make use of these things, but well, we'll have to figure out exactly how we want to use them. Okay, thanks a lot.
Yeah, Attila, we do have the capability currently for on a smaller scale using launching interactive Jupyter notebooks on these GPU systems. We have dedicated Atlas systems for that we plan to be expanding soon as well.
Okay, thanks.
Thank you. Are there any more burning questions for me or Torre about BNL? If not, then I'll thank Torre again for this very interesting, comprehensive talk. And we will move on to Graeme, who is going to tell us about the past year at the HSF and CERN and looking forward into 2023. Let's take it away, Graeme.
Yeah, thanks a lot, Ofer. So indeed, I'll present some of the highlights that we had in the HSF in 2022 and give you some hints towards what we might be tackling in 2023. I have to say that the 2023 plans are still very much in development. One of the things that we do in January each year as we have discussions with the working groups about what it is that they would like to achieve in the coming year. And that process has only just started. So I can give some hints of directions that I think we'll be going in, but it's far from a complete view of what will happen in 2023. But okay, let's move on. So just a quick reminder of the HSF organization and what its role is. I mean, so we're here to really catalyze and enable common software efforts across high energy and nuclear physics. And we've been growing our interaction with the nuclear physics community in the last couple of years, of which this forum is one of the prime examples. And just a caveat, of course, is that we're not a funded organization, so we don't own or allocate resources ourselves. And all of the work that I discuss here is really owned by the experiments, projects, teams, whoever it is that is doing it. But we are enormously grateful that many people in the community take the time to contribute to the HSF. And to share and grow their work in that wider context where they sort of maybe break out of the little project or experiment silo that they might be in. So organizationally, we have an HSF coordination group that provides oversight and drives overall engagement across the community. But the real things happen actually inside the working groups and the activity areas, of which we have quite a number, focusing on different 8 topics. I'll give the list right at the end of the talk, actually. But the idea here is that they're focused on one particular area, and then they'll organize activities around that. So the HSF's role is mainly one of an information conduit and a kind of meeting point for people interested in similar topics to come together. So reports on interesting and common work being done, technical comments and discussion. We of course encourage cooperation across different experiments in different regions. And we do motivate very much the publication of summary documents or papers that can be very useful references for the future. So a little bit about 2022. I was looking back at the previous year's talk that Benedict gave, and I was trying to like, yeah, COVID was like a serious impediment to everything that we did all the way through 2021. And I think in 2022, we saw a gradual easing of restrictions related to COVID. I mean, we're not over the pandemic by any means, but we did see in-person workshops and conferences could start to happen again from about the spring of last year. So iChep happened in July with a significant software and computing track. ACAT happened in November, so many people were able to travel to Italy. And of course, it's not just the conferences. More people were able to travel and meet with colleagues. Experiments resumed their in-person events, and it was great to see many colleagues around there. And I think that really helped everybody to reintroduce a much needed face-to-face coffee time, beer drinking dimension to activities, which is really important for the long-term health of our community. And I was really pleased in particular to see things like student activities start up again. For instance, we had, for the first time in a couple of years properly, we had the CERN student program with all of the students here. That said, of course, post-COVID, the world isn't the same as it was before. I think virtual participation has become accepted for almost all events now. So the hybrid model is the one that we have, where you somehow balance certain costs in terms of time and finance and other matters versus the quality of the interaction. And I think one of the things that we're driving for in the community, of course, is to reduce our environmental footprint. Computing is one area where we're attempting to optimize, but also, of course, we spend a lot of time in carbon dioxide traveling. So when we do fly, we should really try and maximize the benefits that are enjoyed. And we take the train if we can. Okay, so the HSF and partners have always had a strong distributed dimension because we're very much an international organization, and we continue to benefit from that, but very much, I think, backed up by in-person interactions as well. Okay, so turning to more specific activities, I mean, one of the goals of the HSF is to advocate for the importance of software inside the community. And there was quite a few talks at conferences and events that helped us to do that at big international conferences like Lept and Photon, at kickoff workshops for different projects like SmartHEP and SwiftHEP. And at policy-making bodies such as the Jena Symposium in Madrid in May. So I think that's one of the really great things about the HSF is it's now recognised as a place which you can come to, and we will argue and tell you why software is important, and that gets more of an echo. Of course, this year as well, there was the slightly delayed snowmass process that happened, and people involved in the HSF submitted quite a number of papers and letters of intent to that process, particularly our US colleagues who were involved in making sure that software and computing had its place in the various snowmass frontiers. And one of the things that we regularly do is through the HSF, we give input to the LHC committee at CERN together with WLCG. That's very important to keep software and computing in the minds of the people making decisions about how our community gets resourced. One of the things which I enjoyed a lot last year was that we had a very rich program of workshops in 2022. The HSF co-organizes these in many cases with other partners, and I think that's really important because it's a way of reaching out to other areas inside the community. And it's also a way of using the HSF as a mechanism to bring people together and to discuss. So I'll actually spend quite a lot of the rest of the talk talking about these different workshops because I think they were high points for the HSF and for those who were involved. The detector simulation on GPU community meeting, we had that back in May. Then later on in May, we had the Analysis Ecosystem 2 workshop in Paris. Once again, hosted the PyHEP 2022 online workshop. And more recently, I think back in November, we also had a workshop focusing on software citations and recognition, which is a really important part of our work in the field to make sure that we elevate the recognition of software. In addition, we had the future trends in nuclear physics computing. I'm not going to talk about that one because I assume that most people here were probably attended that one and were involved, so no need to repeat that. And also our event generators group and the HSF supported the MC4 EIC workshop that happened towards the end of last year as well. So that one I also will mention much further. Okay, so let's go to the detector simulation on GPU community meeting. We already touched on this actually talking about GPUs in the Torre's presentation. Of course, there's a lot of interest in using these to run HEP workloads. So as they become more generally available, facilities, can they be used for, in quotes, maybe generic HEP workloads? Now, simulation is an obvious candidate in one sense, simply because it consumes huge amounts of resources for the LHC experiments in particular. And as a result of that interest, there are two R&D projects in place to look at aspects of particle tracking on GPUs. One is the ADEPT project, which is based in our SFT group here at CERN and with UK SwiftHEP support. And then there's the Celeritas project at Oak Ridge. So those projects had been running for 18, 24 months, and it was a very good time to meet together, see what we'd learned and see what the prospects were. Really asking the question, can we make HEP particle transport efficient enough to be usefully run on a GPU? How far away are we from a production level tool? And what changes would be required to port key elements of user code so that these things actually work for the experiments. So this is not an easy problem, by the way. GPUs like homogeneous workloads, but particle tracking is inherently stochastic and divergent. GPUs want memory accesses to be uniform, but the way in which we implement our geometry models is not very friendly towards that. They're traditionally indirected and hierarchical. And of course, the whole process of the simulation, particles being created and then being killed off, needs new memory and creates holes in memory structures, respectively. So that's a real challenge as well. So the project both presented their status in terms of physics, and here you have a tension between physics capabilities and divergence. Essentially, the more physics you put in, the more divergent your workflow can be. But obviously you want the physics to be capable enough so that you can really trust the results. I have to mention here that then the focus actually goes towards electromagnetic calorimetry, which is the key area in terms of CPU consumption for most of the experiments. Actually, and it also naturally limits the physics scope that you have to introduce. Geometry and magnetic field. Geometry, as I said, is a particular bugbear. Magnetic field is important as well. Very easy if you have a uniform magnetic field, much less easy if you have an inhomogeneous magnetic field that might require interpolation and lookups and all the memory access issues which are going to crop up because of that. And there was some discussion of integration, how to write the scoring code and prospects from that. So the project status, and this was from back in May, things have moved on a little bit since then. Really, both projects are able to demonstrate, let's say, comparable performance for certain workloads on similarly priced CPUs and GPUs. However, one notices that the performance drops a lot on realistic geometries. And that's pointing the way to R&D, which is going on now, in particular towards new geometry code, which is surface-based rather than volume-based. Celeritas gets similar performance to Adept, and on the very, supposed to be GPU heavy nodes in HPC centers at Oak Ridge, they're actually getting about 40 times increase in the events per second by using the GPUs compared to the rather modest CPUs which they have. So there was lots of ideas which were shared between the projects. There's very good communication. There's not really any code shared yet. I'd say we're still at an R&D phase, but I very much hope that that does happen later on. And we do foresee another status update meeting between the two projects this year. There's quite a lot of things also happening in simulation which are going on in parallel. And for instance, the development of sub-event parallelism project, which is leveraged heavily by the East application, is going to help a lot with the scheduling of code on the GPU. That is happening in concert with obviously a good chunk of the simulation still running on the CPU. So let me move on from that one and talk about the analysis ecosystem workshop that we held at JLab. So we had 70 people there attending in person, which was fantastic actually to be there with colleagues that many of whom I hadn't seen for several years. This was 5 years after the first workshop in Amsterdam, and we focused on various key areas for analysis, the facilities, machine learning and differentiable computing, trigger level real-time analysis, the user experience and declarative languages that users might use, the discussions on reduced formats and specialist inputs, so things like nano AOD or FizzLight in tuples. Metadata, bookkeeping and systematics are something that is very important to do right. Otherwise, it causes a lot of pain for the analysts. So high luminosity LHC, of course, was one focus, but not the only one. I mean, run 3 for ALICE and LHCb is a significant challenge, as well as Bell 2, June, and so on. So the summary, I think, of the workshop is that a lot of the analysis facility prototypes look fast enough, and the real area that needs work on is ease of use. But here come many questions about scale out, authentication, complexity of deployment, how users get feedback. And this is something that we continue to look at through the Analysis Facilities Forum inside of the HSF. So machine learning, of course, is much more widespread in the community. It's becoming easier than it was a few years ago, but it's still very dynamic. Auto differentiation is extremely interesting, but I think its utility in the field is not yet clearly established, although there are some promising hints. And there was a real need for standard benchmarks to actually measure performance in a meaningful way. User experience to reduce boilerplate and tackle error, well, avoid error efficient code was discussed quite a lot. Quite some differing opinions on how much software engineering we need to teach physicists or how much they might be willing to learn, but certainly there's some training which is needed. And improvements in bookkeeping and systematics are really needed. And the new .vary method inside of Roots, our data frame, looks like it's a very useful way to try and do that. So interoperability as well between different ecosystem pieces is inconsistent and should be improved. Reduced formats are going to have to be used, so NanoAV and PhysLight, as I already mentioned. But how do we support other analyses that require custom formats or dedicated skims? And there's an active discussion now, Torre mentioned the new RN tuple format, about ways of augmenting RN tuples with different pieces of information without having to copy everything over again. So that's an active R&D area. So bookkeeping and systematics was discussed mainly in terms of user experience, and there's some prospect that we might undertake some kind of systematic challenge, as well as following up on the very useful observations which were made in the metadata paper. The workshop outcomes are actually now available both on Zenodo and on Archive. So things like making columnar analysis easier, focusing on tool interoperability, encouraging open data sets, which are really important for performance evaluations. We do still hope to follow up on the metadata matters later on this year, possibly starting with the Birds of a Feather meeting at CHEP. And systematic uncertainties, as I said, remain a major pain point. So common tools to make this easier and tackle them in multiple experiments are something that's important. Analysis facility work will continue. I already mentioned the Analysis Facilities Forum that tracks this and also works closely with our colleagues, for instance, in Iris Head, who are undertaking their Analysis Grand Challenge. So terribly useful workshop, and if you haven't read the conclusions yet, I would really strongly recommend them to you as a good guide to the kind of things that we need to do in the next couple of years. Let me turn to PyHep. So we started this workshop series in 2018, bringing together developers and users, recognizing both opportunities from Python-based data science tools, but also some rough edges where a need to smooth things off to create a coherent ecosystem was really necessary. And the first two workshops were in person. They had about 70 people. And then from 2020, of necessity, the workshop went online, where it hit this amazing vein of enthusiasm and popularity with more than 1,000 people registering. And many of these were students who were keen to learn. And so the workshop pivoted a bit to introduce more didactic elements. Now, that seemed to be a useful thing to continue with. So in 2022, again, we had the workshop online. We had 420 people come through the course of the week, but that was a lot less than the 1,000 people who registered. So somehow I think we started to see that free online events have a relatively low commitment, and as we move out of the pandemic, perhaps people are less inclined to spend a lot of time online. Was a good place to try out some novel forms of engagement, so using Remotely Green as a networking tool, and a hacker shop where we tried to encourage new developers as well. So some of the highlights were surveys of use of the Python in the experiments, some of the really important tools which have been developed like uproot and awkward array, interfaces to standard things in C++, so the Python interface to HepC3, and of course training is very important as well. We discussed that a lot with the HSF training group. So this year, we'll definitely hold the virtual PyHep general workshop again. But we realized that we missed a little bit the discussions which happen between developers, which really push the tool sets on. So we would like to have an in-person developer-focused PyHep dev event as well. Let me talk a little bit about software citation and recognition. So this was a workshop that was organized, actually kind of came up in a number of places at the LHCC and in IRIS-HEP reviews, was really, are we helping in this area? So we thought we'll organize a workshop to sort of get the state of play here, come up with some recommendations. So review the status of citation in HEP, how we can give credit to software developers and maintainers, provide better and more sustainable software, and support reproducibility. So there's quite some work has gone on here in the last decade. So the Force 11 group talked about the importance of credit and attribution, identification of software, persistency, accessibility, and specificity. And one of the key things that came out of that was, I suspect that some of you will have heard of it, this citation format file standard that you can even upload onto your GitHub repository now, and the code meta standard for a richer description of the software which you write. In terms of what to cite, we had a very interesting discussion about whether should software just be cited as a traditional academic paper, but there are certainly some issues there. People who write software maybe sometimes don't like to write academic papers, and then you can have the situation where ancestor papers are picking up all the citations. So the original Géant 4 paper gets the most citations, even though the code today is almost completely different and all the recent authors and contributors are missing. So somehow these people are not getting proper credit for the work that they've done in modern versions of Géant 4. You could cite the software itself, so you can get a Zenodo DOI for a software release, but this isn't very well rewarded academically. And it doesn't describe why the software exists or the design choices that were made. So there are some nice developments around things like the Journal of Open Source Software, which combines the code with quite a short paper which describes the software. And they will, if you try and publish there, review your code and your repository as well and check that it meets some best practice standards that would allow people to really effectively use your software. So for the moment, that looks like a nice sweet spot. We're developing advice for developers about how to make their software certainly easy to cite. We had a very interesting discussion with experiments about the desire for some consistency in citation recommendations, which can actually vary quite a lot, even among the CERN LHC experiments. So perhaps the HSF will curate that. And we heard about some really nice developments from Zenodo and Inspire, who are actually going to better support software citation in the coming year and actually start to track software citations as well, which will be at least one mechanism for giving credit to authors. So we're preparing the conclusions from that workshop now. I would expect that they would be ready in a couple of months. They will be summarized in a nice paper. Changing theme a little bit, I wanted to talk about GSOC in 2022, where we participated as an umbrella organization. So it's kind of a service to the whole community. After a change in 2021, which we didn't like very much, where all the projects became short, Google decided you can have short and long projects last year. And we again had a rather good turnout from the community. We had 27 funded proposals who got a student out of 27 proposals got a student out of 41. That was 26 different organizations and 18 different projects. Unfortunately, this year, and maybe it's just statistical fluctuation, we actually had more failures than other years, with a few students withdrawing and 4 of them not really performing up to scratch. They did relax the participation requirements last year, and perhaps that affected actually the quality of the candidates. So it might mean that this year we need to be a bit stricter about making sure that we do take very good students. However, the program will run again with a mixture of project durations. We will get started on this very soon, so please look out for an announcement from the HSF that you'll be able to write your project proposals. And this year there'll be a change in the CERN HSF administrators. So Andre and Antoine stepped down after many years of service. Thank you to them. Benedict will be one of the organizational admins, but he needs a couple of people to help him. So volunteers would be very welcome for this valuable task. I really wanted to mention the training working group, though, just to highlight another very successful activity in the HSF. So thanks to Killian for the theme of this slide, where he lists all the achievements unlocked by the training working group. You can see all of the things that the trainings that they ran last year, and things which are upcoming even now, with analysis preservation training running even as we speak, software carpentry training next month, and in addition of the C++ training, which is a very popular training course, which will be run at JLab after CHEB this year. So that's nice to see that training becoming in person again, which the students benefit from enormously. I'll close a little bit with a mention, shout out to the working groups. We have a lot of working groups and activity areas which are led by enthusiasts and advocates for common work. Torre gave a nice slide on the work that the conditions database group are doing with some of the BNL experiments. These were really active in 2022, many useful discussions. I just could not go through them all, but take a look at their Indigo categories for more details of the meetings and the topics which were covered. So let me wind up now. So in 22, the HSF colleagues were involved in many events and discussions on important topics, reinforcing the idea of the HSF as a place where the community can gather. We hope that's really useful to people. It certainly seems to be. This, of course, then feeds back into the work which is tackled by the software projects, because they get better feedback on what the needs are. We do try and encourage diverse R&D, but also work closely with the experiments to ensure that what we deliver are very practical solutions. And let me make just one highlight announcement for 2023, which is that for the first time since 2019, we'll be able to have an in-person WLCG HSF workshop before CHEP in Norfolk, of which the topics will be the analysis facilities and heterogeneous computing, two very nice crossover areas between software and computing. So I'm certainly looking forward to that, and make sure you sign up for that workshop at the same time as you sign up for CHEP. And I think with that, I'll finish up for now.
Thank you, Graeme. Thank you for that fascinating overview and for all the work that HSF does in organizing all these efforts. And I'm particularly pleased to see the focus on the analysis facilities and heterogeneous computing that we're planning for CHEP. Are there questions out there? I don't see any in the Google Doc currently. Is there anyone who would like to ask a question?
I like that it says on the pre-workshop, non-x86 and heterogeneous computing.
Yeah, that's right. That's right. I mean, you mentioned ARM, Torre. Yeah. I think that's a very valuable platform for the future. And yeah, so, you know, if we're going to port our software to ARM or Power or anything else, then there's a whole set of things that need to be built into the experiments build, validation and deployment workflows to support those architectures, as well as the more exotic GPU type of solutions.
Hey, Graeme, it's like I said, it's nice to see this with CHEP, and it's going to be, you know, sort of near the JLab facility. Have you all this work on analysis facilities? I know the focus has been on HLLHC mostly, as you mentioned, although some other groups in there too. And I know that there's you know, similar work sometimes goes on in the photon community here. But I'm wondering, have you seen much growth in interest, for example, in NP, or is there anything that we can say about that? Because you know, NP always seems to be ahead of the game, I think, a little bit on maybe use of ML techniques and that sort of thing. And I'm wondering if there could be more integration with that community in these various forums that exist now that have been very helpful.
Yeah, we certainly had people who were not from high energy physics along at the analysis ecosystem workshop in Paris in May. So there are certainly some contacts that have been made there. And I think as you see other experimental communities scale up, the kind of things that we're talking about with respect to analysis facilities do become more and more generally interesting. And there are some very specific things, although I think largely shared between high energy and nuclear physics, in terms of the front end software, let's say, that people would be using to power their analysis. But a lot of the back-end topics would be very much in common. And I think there are certainly some interesting discussions that we could have with other data-intensive sciences as well. So yeah, let's see how that goes. I'd certainly be very open to discussing with other communities. I think if I remember correctly, there have been some discussions of that actually in the Analysis Facilities Forum. I think I remember seeing some presentations from IceCube there, and maybe from KM3Net as well. So there are some links at the moment, could be developed, I imagine.
All right, thanks, Graeme. Are there other questions before we let Graeme go? If not, then I'll thank you again for this excellent presentation. And we will move on quickly to Brad Sawatzky from JLab, who will look back at the year at JLab and give us his perspective also for the future.
All right. Thank you very much. So yeah, I'm going to try and jump through this very quick. Of course, the scope precludes jumping into any of these topics in any detail. So forgive me in advance for glossing over a lot of these very complicated and interesting projects. Just, trying to give you a flavor and a sense of what we're doing at JLab and where we're going. Before I move on, I just want to call out and thank a number of people in particular: Marcus, Brian, Graeme, Makoto, David, and all of the others whose slides I am using. Those are the folks, of course, that are doing the heavy lifting on all of these things. So to begin, we'll kind of start on the hardware side, just a brief update or status of the JLab data center. At the moment, we've got something on the scale of 6 petabytes of storage across 2 Lustre file systems for use with large data files, data streaming from the halls, and the analysis output, another 5 petabytes on ZFS, backing some NFS shares and the XRD storage that we're rolling out. Tape library is capable of 100 plus petabytes of long-term storage and is scaled to handle the burst rates coming from the experimental halls. On the compute side, we've got 8 NVIDIA A100 GPUs, 56 NVIDIA T4 GPUs available for sort of the general purpose scientific community. On the conventional side, there are the equivalent of 9,000 cores of AMD Milan CPUs in the high throughput farm. And that's a mix of Intel and AMD CPUs across multiple generations, but saw a pretty large purchase last year. And we'll be retiring some of the older nodes fairly recently, if that hasn't already happened. On the Lattice side, the dedicated resources for that program are on the scale of 400 plus KNL nodes, 256 NVIDIA 2080 GPUs, and 64 AMD MI100s. Looking forward, an additional hot aisle containment system was constructed over the last year to increase and improve future capacity in the data center. A 100 gig scientific computing network upgrade was completed. Engagement with the Open Science Grid continues and is ongoing. One of the big efforts last year was implementing the Psi token infrastructure for user authentication. And that's now being tested with the XRD storage. As part of that, and as the OSG engagement sort of ramps up, a number of single points of failure or potential single points of failure in servers and services were identified and addressed, and those projects are ongoing. A couple of things that we're looking at next year that may be of interest to the JLab community in particular are we're working on some plans to improve and encourage the use of containers in the supporting infrastructure, the supporting software infrastructure for the analysis programs in particular in the experimental halls, but it'll be broadly available across the JLab user community. Also deploying a new dedicated high uptime ESX VMware cluster just to support hall operations. So this is something that of course has been in general use on the scientific computing and sort of general purpose computing side for many years, but we'd like to take advantage of the real-time snapshots, backup capability, and high availability, sort of instantaneous failover features that dedicated VM clusters provide. So with Hall A in particular coming online, the SBS program last year and throughout and sort of the fall of the previous year, the data rates from that hall have proven to be on the same scale as Class 12 and GluX, the two other high throughput halls at Jefferson Lab. So that required and incentivized a push to identify bottlenecks and a few issues that prevented effective farm utilization and that were causing some stability issues. So it dovetailed nicely into sort of the last bullet on this slide, where there's been an ongoing project to log and make various metrics associated with farm job utilization available to the general users and to the scientific computing staff to make it easier to not only identify these bottlenecks, but allow the users to see them before we do, so they can sort of proactively take care of some of these issues and get their jobs through more efficiently, but also allow us on the scientific computing side to identify these issues and solve the underlying constraints, or to build out or improve the software algorithms that are supplying both data and that are distributing jobs across the farm. One of the big themes that you'll see throughout the rest of the talk, which is more focused on a number of software and integrated hardware related projects, is the emphasis towards working towards the EIC. Now, of course, this dovetails nicely with the existing JLab program, but with Jefferson Lab and Brookhaven being the host laboratories for the EIC experimental program, this vision and the needs of the future EIC are very much directing what we are doing, both for the JLab 12-bit JEV program, but making sure that we have the personnel, the knowledge base, and are accomplishing or investigating some of the research that will be necessary to execute the EIC program as envisioned. So, of course, software and computing, as we've all seen, are an integral part of our research. That is only growing. The little survey here of PhD, nuclear physics PhD students, so 80% of their time, the question is, what fraction of your time do you spend on the software and computing aspect of your research? And it's on the scale of 80%. That's a big number. So this just highlights the importance of, user-centered design. We need to be able to on-ramp these folks and to streamline the path from data collection from the DAQ all the way through to the physics analysis and the sort of the publication, which is what contains the final insight, the knowledge of the underlying system, the insight into the underlying nuclear system that we're trying, that is the goal, the fundamental goal of all of this. So the EIC distributed computing model has the data collection happening at the EIC in echelon 0, And nearly all of those data, raw data, reconstructed data, simulated data, gets streamed out across the Echelon 1 sites that includes Brookhaven and Jefferson Lab. And in order for that to work effectively and to work in the context of the software and computing vision that I just sort of highlighted, that requires a lot of things, a lot more work to be figured out. So we need a resilient and reconfigurable data transport layer. If we're going to be pipelining data straight from the detectors all the way through to an analysis structure or in a stream and readout context, that puts a very high premium on the data transport layer being reliable, being self-healing. And some of these ideas are being researched within the context of EdgeFat and Iriad. AI ML supported systems management. I'll touch on all of these in very briefly as I go through my slides. So just at a very high level, there's a new LDRD to focus on to take advantage of AI ML in a data center reliability context. There's some existing programs, AI for experiment configuration and control, or calibration rather, and control. Hydra, a program to monitor and do anomaly detection on the detectors, particularly at JLab, but it's an extensible framework. Studying challenges with integrating research infrastructure across distributed sites, intrinsic to the butterfly model, this distributed model for the computing that we're looking at with DIC, but of course to various degrees, we are already distributing data across multiple sites, within the OSG, even just within our JLab community. Streaming readout and data analysis R&D associated with the streaming readout model. This includes development on the JANA analysis package I'll touch on, and AirSAP is underway. Talked about, taking better advantage of heterogeneous architectures, GPUs or non-x86 CPUs. FASM is a project that I'll touch on that is very interesting. Addressing challenges of autonomous control and experimentation as the detector systems become more and more complicated, and we want to use these detector systems as effectively as we possibly can. There are a variety of projects involved in applying AI ML along the lines of AIEC and others to provide some sort of autonomous control of these detector systems. And that's covered in part within the Indra Astra program. And of course, on a sort of a broader overarching scale, if we're going to be using distributed and shared resources, we need to have a federated approach to handle and authorization and access to these resources. And as I mentioned, containerization and distributed software shares are intrinsic, again, along with the authorization to a distributed management or distributed computing infrastructure that is being rolled out now and is certainly envisioned to be in full stream for the EIC. Near term and supporting those goals is rolling out XRD and Ruscio within Jefferson Lab. And that's one of the projects that XRD has been in process for a while at Jefferson Lab. Ruscio, we've got some test beds that are being set up late last year and will be getting rolled out in an experimental, or not an experimental approach, but in a test approach with an idea of rolling it out further within the JLab community. So Indra Astra, the goal here was to develop a prototype for a fully automated responsive detector system as a step towards a fully automated self-conscious experiment, something that can adapt to changing conditions on the fly. And this involves a host of projects, some of which I'll touch on later in the talk, including JANA 2, the analysis framework. So one of the interesting bits associated with Indra Astra is they had a small gem here as part of the test bed, and took a look at sort of a proof of principle approach on streaming readout and doing some real-time detection and change detection and calibration or baseline shift recalibration. So this is the ADWIN bit here, where The data here are coming from the gem and identifies the system identifies a shift in the baseline, which is something that happens with the gems in the current when the current gems that are currently deployed at the lab. And this system was able to do a full recalibration on the fly. Touching on JANA2, I think this is a relatively recent decision, but JANA2 has been selected for the EIC EPIC detector. So JANA is a multi-threaded reconstruction framework project focused on GlueX, or at least I think that was the initial driver for it. So it's got a couple of decades of experience behind it. JANA2 is a rewrite incorporating modern computational science practices. Taking a lot of the lessons learned from JANA and developing a system that's got the legs to carry us forward into the EIC, in addition to being used in some of the upcoming projects at Jefferson Lab, some of the 12 JET programs. So just coming through some of the other items that I called out on my initial list, we've got EdgeFAT. This is the ESNet JLab FPGA accelerated transport. The goal here is to prototype dynamic steering of streaming data. So the data format itself contains metadata describing its content, and then the underlying infrastructure is able to route that content in real time to provide, in flight. For example, if the system architecture reconfigures, you need to do load balancing or there's failure, and allows the remote data source to be agnostic of the destination hardware configuration. So the goal being, dynamic, intelligent steering of the data. You can see where this would be advantageous within the butterfly model, for example, if you've got streaming readout and you have multiple distributed sites, being able to collect those data and do further processing. This project, the EdgeFAT project, is being extended with a recently approved LDRD under the title Integrated Research Infrastructure Architecture Demonstrator, or IRIAD. And it builds on the EdgeFAT program to deliver a demonstration system with the features noted here. This will demonstrate a core technology for a high-performance data facility to handle critical, time-critical science use cases and capability to stream data between detectors and data centers at geographically diverse sites with, the future EIC, Brookhaven, JLab butterfly model in mind. Sort of connected to that is another research program called Giraffe, another LDRD funded recently approved program. That's JLab integrating research infrastructure across facilities. And the goal here is, again, sort of simplifying things for the end user. The idea would be to study the challenges of heterogeneous, distributed, and opportunistic compute resource provisioning. So you've got a bunch of back-end resources available across the world in different data centers, both commercial as well as nuclear physics and HEP data centers. But you'd like to be able to present all of these to the end user as a single unified computing infrastructure so that they don't have to worry about, where specifically is this going to run. That allows, the system as a whole to be able to bring in and take advantage of unallocated or idle computer resources from various providers, sort of in real time, in terms of the load balancing or load distribution sense. With all of these data centers, in JLab in particular, but as they become increasingly